As we saw in part 1, freestanding statues are raised with pedestals attached. Using 3 levers, the whole assemblage, including a pedestal, is raised into the air. Obelisks differ in that respect, because all obelisks stand upon a separate pedestal, and all of these pedestals have a groove cut into the top. It's widely accepted this groove is an aid to its construction, providing a point of engagement, preventing the obelisk from sliding across the pedestal. In many cases, the height of the obelisk was also increased by placing the pedestal upon a foundation. Made from several granite beams, this foundation is locked in position with dovetail joints. The foundation also increases the footprint, distributing the load over a wider area. If the obelisk was raised in a similar manner as to the statues, in other words, raised from the ground and then lowered towards the pedestal, at the start of construction, the obelisk would cover the area where the pedestal would have been. One can only conclude the pedestal and its foundation was placed in position after the obelisk was raised into the air. Now this is counterintuitive and probably the reason raising the obelisk has been a mystery for so many years. Previous attempts at solving the mystery have involved constructing long ramps to a fixed pedestal. The presenters of the TV programme Lost Empires Raising the Obelisk, produced by Nova, their obelisk was hauled up an embankment to a precise point over a sand-filled pit. This point was determined by the obelisk's centre of gravity, and it was there the obelisk would rest upon a wooden axle. Brake ropes held the obelisk in position while sand was removed from beneath. The obelisk rotates around its centre of gravity and heads towards the turning groove. And once the butt of the obelisk engaged into the groove, a system of ropes and stays were used to haul the obelisk into its final place. Although ungainly, the system worked. Importantly, hauling the obelisk up the embankment was tested with ropes and an A-frame, but failed. Now, I wanted to solve the mystery through experimentation, so I constructed a model of the remaining obelisk, Ramesses obelisk the second at Luxor, and the other stands at Paris in the Palais de Concorde. The model was made using thin plywood, and the material was very light, so to increase its weight I filled the void with sand, and when full the obelisk weighed 7 kilograms. The obelisk was 1 metre in length, and I scaled the rest of the building to it. I constructed the pylon wall, the pedestal and foundation, and finally the flagpoles. Now my first instinct was to find the obelisk's centre of gravity and mark that point. The desired angle for lowering the obelisk to its turning groove would be around 45 degrees, because as the obelisk rises up from that angle, you require less and less effort to reach the vertical. I outlined the silhouette of the pedestal and the pylon wall, and then drew a line up at 45 degrees. The line intersected the top left side of the pylon groove. The grooves in the pylon wall were known to have held flagpoles. Now, the Egyptians were renowned for repurposing things, and I was confident that they used these flagpoles as levers, and I worked on that assumption. As with the statue experiments, the safest way of lowering the obelisk would be from a fixed point, above the statue's centre of gravity. Now, if the flagpoles were used as levers, the ideal position for the obelisk's centre of gravity would obviously be between the 2 levers. The load would then be distributed evenly over each. Now, there's something strange. It's been noted that both the Luxor obelisk and the one in Paris have both been observed to have lateral surfaces that are not flat planes. The northwest and the southeast side of the obelisk have double curvatures. Laterally, they are both convex, and the verse side of this convexity, the former being 28.57mm and the latter being 38.01mm. In other words, these 2 sides have been rounded out. And the longitudinal sides are remarkable, that in the northwest face is convex by 20.32mm and the southeast is concave by 12.7mm, making the vertical ever so slightly bent. Now, Henry Honeychurch Goringe stated that this imperfection can hardly be attributed to accident or by the imperfection of quarrying and dressing, but must be considered one of the many questions connected with this monument that have yet to be solved. D.T. Arnold pointed out that one cannot help but wonder that the great creators of the older obelisks in the 12th dynasty, they perfected a way of carving the obelisk with flat surfaces, suggesting the quarrying techniques have been taken a step backwards rather than advancing forward as technology usually does. Now I can demonstrate that this design is an advantage and not a step backwards. So to the first question, why is the obelisk slightly bowed? Now imagine the obelisk as part of a rounded tube. Place the tube balanced between two levers and move the levers up and down, and a tube falls off and safety is compromised. However, put a slight kink or bow into the tube and repeat the experiment. The tube returns to its original position. What the Egyptians are doing here is using the obelisk's centre of gravity or centre of mass to stabilise itself. Question 2. Why is the obelisk rounded out? The answer is quite simple. When a lever raises a load from a flat surface, all 7 kilos of the load rotates around the fulcrum. However, put a slight roundness to the surface and the load is lifted vertically. The load is balanced between the two levers, so it requires half the force to lift the load. I can demonstrate this with an experiment. So that's just about enough weight to move the obelisk, and it actually weighs 313 grams. So that's 313 grams. So we'll empty that in there again. Turn the obelisk over. And try it again. Let's even moving it now while it's empty. And that weighs 159 grams. To work out the force required to lift the Luxor obelisk, which weighs in at 227 tons, we can use the model to find the mechanical advantage. To do this, we divide the force used on each lever, which is 139 grams, by half the weight of the obelisk. Now the obelisk actually weighs just under 7 kilograms, it's 6.9 kilos, so half that weight is 3.45 kilos, divided by 139 grams, and the answer is an MA of 24.82. So an input force of 1 ton would give you an output force of nearly 25 ton. So divide the weight of the Luxor obelisk by 2, which equals 113.5 tons, and divide that by the 24.82, and the answer is 4.57 tons per lever. It's vital the obelisk's centre of mass is positioned exactly between the levers, and that its rotation point at the top of the lift has been established. Once the lift has started, there's very little you can do about moving the obelisk into a different position. To get the obelisk to the construction site and position it, the Egyptians used a machine called a cherubim. I'll leave a link to the cherubim's design and method of movement, but basically, to move a statue or obelisk, the Egyptians transferred the mass of an object from one side to another. Now imagine you have a large slab of marble, say 5 foot high and 3 foot wide and 2 inches thick. It's heavy enough for you to stand it on end, but it's too heavy to carry or lift off the ground. By instinct, you push and raise the load onto one corner. Now once balanced, you rotate the slab a quarter of a turn. You then use the slab's own weight with some slight assistance to stand it up on its opposite corner. Again, you rotate a quarter turn and walk the slab forward. In the same way, the cherubim rotates the mass of an object from one foot to another. The cherubim machine is a design I came up with after reading Ezekiel from the Old Testament. Now with all this information, we can set about constructing the lifting compartments. The lifting compartments would obviously be positioned so that the weight of the obelisk is distributed evenly over each lever. The size of the magazine is dependent on the distance between the levers. This main compartment straddles either side of the obelisk's centre of mass. This supports the main body of the obelisk and would be sufficient to hold the obelisk aloft. However, you would require further magazines, one either side of the lifting compartments, as additional support to strengthen the columns. As before, height is gained by forcing the levers down and filling the void under the opposing fulcrum with sand. Cross beams are then added to the compartments to support the increase in height of the sand. And as the obelisk rises, the blocks are used to contain the sand and the reed mats. The reed mats and the sand support each other, so there is very little lateral movement. So there's no danger of the walls collapsing. And once the obelisk has reached the required height, the lever is removed and the first stage of the lowering process can begin. The beams in the right column are removed and the sand falls to the floor. Now the blocks surrounding the first magazine are dismantled and the sand is discarded from the column. The sand discarded from the column is used to cushion the fallen blocks. The mats are separated and set aside for reuse. At this time, the central magazine is sufficiently strong enough to hold the obelisk aloft whilst this work is carried out. With the levers removed, there is sufficient room for the axle to be tethered to the obelisk. This axle is bound tightly to the obelisk above the left central lifting compartment. Its vitless axle is bound firmly to the obelisk because the obelisk will rotate about this fixed point. Once the first magazine has been dismantled, the foundation assembly can begin. The foundation blocks are of sufficient size they can be manhandled into position, then joined together with the dovetail joints. The pedestal is then mounted upon it. Measurements are then taken from the axle to the base of the obelisk. This measurement is then transferred from the axle to the pedestal turning groove. As the obelisk nears the turning groove, any discrepancies between the butt of the obelisk engaging into groove can be taken up by moving the pedestal slightly forwards or backwards. And by looking at the sockets cut into the bottom of the pedestal, that's exactly what they did.